Hi everyone. Today we're going to take a look at how to determine the empirical and molecular formula of a compound. So before we get into what an empirical and molecular formula are, we need to understand what exactly a chemical formula tells us. So the subscripts in a formula are essentially a ratio of the atoms in a compound. So it just tells us how many atoms of each element are present in that compound. And it just kind of gives us that ratio between them. But it can also represent a ratio of moles. So take an example of this compound, C3HAO. In one molecule of this compound, I have 3 atoms of carbon for every 8 atoms of hydrogen and 1 atom of oxygen. Now, if I had 1 mole of this compound, then essentially I would have 3 moles of carbon for every 8 moles of hydrogen and 1 mole of oxygen. So those tiny little numbers at the bottom, the subscripts, will either tell me the atoms of these elements or the moles of the elements and provide just a ratio within the compound. So an empirical formula is just the simplest formula of a compound. Essentially at this point, all of these subscripts have been simplified to their lowest ratio. Now, since we took a look at the fact that those subscripts represent ratios of atoms and moles, finding the empirical formula comes down to determining the moles of these elements and what those ratios are. By taking the percentages that were given in a percent composition, we are able to find out the chemical formula of a compound. But there's a few steps to follow. The first thing we want to do is, regardless of the compound, we want to assume that we have 100 grams of it. By assuming 100 grams of the compound, those percentages that were given will be equivalent to their masses. Secondly, like I mentioned, the formulas are a ratio of their moles to one another of the different elements. So we'll want to convert our masses into moles. So by converting into moles, we can now begin to find our ratio, which is our third step. To ensure that the smallest ratio that we get is a 1-to-1 ratio, we're going to divide all of our moles by the smallest that were given. This way, we can't have anything less than 1 because, of course, the minimum number of atoms you can have in a compound is 1. When we divide by our smallest number of moles, we're looking for whole number ratios, but sometimes we won't get whole number ratios. So we'll just want to make sure that we can multiply, either get whole number ratios, or we'll have to multiply by some factor in order to turn them all into whole numbers. Those ratios are going to be the subscripts of the chemical formula, and so once we get them, we can write the chemical equation. The chemical formula. So let's actually put these steps into practice and see what exactly they're telling us to do. So here's an example question. Determine the empirical formula of a compound that is 63.5% silver, 8.2% nitrogen, and the remaining mass is by oxygen. So we're told here that this compound is 63.5% silver and 8.2% nitrogen, with the remaining being oxygen. Well, because these 3 elements make up the entire compound, all 3 percentages should add up to 100%. So if I have 63.5% silver and 8.2% nitrogen, I must have a remaining 28.3% oxygen in this compound. So going back to our steps, we're going to first assume that we've got 100 grams of the sample. So if 63.5% of the sample mass is silver, well, in a 100 gram sample mass, I would have 63.5 grams of silver. By using 100%, we can essentially just convert these percentages into grams. Now, the reason why we want grams is so that we can begin finding our mole ratios. Now that we've got grams, we can convert them each into moles by just dividing with their molar masses. So I'm going to go through for each of these elements and convert them into moles. So for silver, we're going to have 0.588 moles. For nitrogen, we're going to have 0.586 moles. And for oxygen, we'll have 1.77 moles. Now that we've got the moles of these substances, we can go ahead and take a ratio. So we're going to take the smallest number here, which is 0.586, and divide them all by 0.586. At this step, we want to be able to round these ratios to the nearest whole number or the nearest multipliable factor. So when I take 0.588 divided by 0.586, that more or less comes to 1. Of course, the number divided by itself is going to be 1. And lastly, 1.77 divided by 0.586 comes close to being 3. So then these numbers, 1, 1, 3, are just the subscripts of our formula. Our formula, we know, contains silver, nitrogen, and oxygen. These numbers that we just found, 1, 1, 3, are going to be those subscripts. So our formula becomes AgNO3. Now that's how we take the percentages and convert them into an empirical formula where we can see that the 1, 1, and 3 are the most simplified. Let's look at one more example of determining the empirical formula of a compound. So here we want to determine the empirical formula of a compound that is 3.2 grams of arsenic and 1.04 grams of oxygen. Now in the last problem we were given percentages to work with and we had to convert them into grams. But this time we begin with a mass and are asked to find the empirical formula. Now even though these masses don't add up to 100 just like they did in the last example, it's not really an issue because we only needed the masses to find moles. If we've already got a mass to work with, well then we kind of saved ourselves a step. So our job is to convert these masses into moles, and then once again we're going to take a ratio. So first let's divide these by their molar mass. So 3.2 grams of arsenic would give us 0.043 moles of arsenic. 1.04 grams of oxygen would give us 0.065 moles of oxygen. Now again, we're going to go ahead and look for the smaller of the two, 0.043. Divide them both by that. We get 1. And then here, we're not going to get 1 or 2. Rather, we're going to get really close to 1.5. So we want to typically try to get to a whole number because, of course, we can't have a partial or a fraction of an atom. But in this case, this ratio is going to be too far off from any whole number. So we're actually going to bring it to the closest multipliable number. And what I mean by that is when we have 1 and 1.5. Well, we need these both to be whole numbers, and I can't just round the 1.5 because it's too far away from 2. But in order to turn a 0.5 into a whole number, I just have to multiply it by 2. Now, whatever I do to one element, I must do to the other. So I must also double the arsenic, which means I have 2 arsenics and 3 oxygens. So our chemical formula would come to being As2O3. You can see that if I did divide both numbers by 2, I would get 1 and 1.5. But of course, I can't have 1.5 oxygens. So right here, this As2O3 is the simplest whole number formula for this compound. So this is something that we will have to do occasionally for an empirical formula. Just multiply by some kind of factor in order to get it into a whole number. The most common one will be 0.5s, but it's the only one. If we had a 0.33, be multiplied by 3, a 0.25 by 4, and so forth. Now that we've covered empirical formula, let's see what's a molecular formula. While the empirical formula is the simplified formula, it may not be the true chemical formula of the compound. The molecular formula is the true chemical formula. A molecular formula may be reduced down to an empirical, And while they may share some common factor between them, the empirical may not be the true correct formula. Rather, it might be just a simplified version of the molecular formula. Now, in order to find the molecular formula, we'll need an extra piece of information. We would need the molecular mass of the compound. So let's take a look at an example of finding not just the empirical, but the molecular formula. Let's determine the molecular formula of a compound that is 54.5% carbon, 9.1% hydrogen, and 36.4% oxygen. And this time we're told that this compound has a molar mass of 88 grams. Since the molecular formula is some kind of multiple of the empirical, we will first need to find the empirical formula, which means going through those same steps that we just went through before. So writing out our percentages, we're going to then assume 100 grams so that these percentages are just grams. Now that we've got a mass to work with, we're going to convert them into moles. Right, we're just following the exact same steps that we were following before, because right now our first priority is finding the empirical formula. So we'll have 4.54 moles of carbon, 9.1 moles of hydrogen, and 2.28 moles of oxygen. Now we're going to divide these by the smallest, divide them by 2.28. And we're going to try to round to a whole number or something that we can multiply with. So this will come to 2, 4, and 1. So right now, our empirical formula is looking like C2H4O. So we can see that this is the simplified formula of 2, 4, and 1. Now, this may not be the true formula of the compound, but rather a reduced version of it. Since the molecular formula may be reduced by some factor to the empirical, it makes sense that the mass would be reduced by that exact same factor. So we would take our empirical formula, C2H4O, and determine its empirical mass. By calculating its empirical mass, which is just the molar mass of the compound, so taking the mass of the carbon, the 4 hydrogens, and the 1 oxygen, this will bring us one step closer to finding the molecular formula. So C2H4O has an empirical mass of 44 grams. We're told the true molar mass of this compound is 88. So if I take 88 and divide that by 44, dividing the molecular mass by the empirical, that gives me a factor of 2. So this tells me the molecular formula is 2 times larger than the empirical, since its mass is 2 times larger. So while C2H4O may be the empirical formula, the molecular formula is actually double that, C4H8O2. We can see that they share the exact same ratio of atoms, the only difference being that the empirical is simplified compared to the molecular. Sometimes the empirical is the same as the molecular, and other times it is not. So that's how you find empirical and molecular formula.